One image, one model, every step done by AI, and I'm testing if any of it actually survives Blender. Welcome to Pixel to Poly, where we test AI-generated 3D assets in a real production pipeline. This is the very first video on the channel, and today we're turning this helmet image into a 3D model and finding out whether the geometry is actually usable or just looks good in renders.
I start in Gemini with a straightforward prompt: photorealistic render, tactical combat helmet, matte olive green finish. I'm not overcomplicating it. I just need one clean, clear image I can actually feed into a 3D generator. Here's a good one to go ahead. Once I've got the image, I bring it straight into Tripo 3D. This is the image to 3D tool doing the actual conversion, so I just drop the render into the upload slot here. Before I generate, I check the settings, texture quality, model settings, then hit Generate Model. And now it's just a matter of waiting for Tripo to build the mesh from that single image. Here's the raw output. 500,000 triangles, way more than I need, and it's all triangulated, which isn't ideal for editing later. I'll flip to the normal map view for a second just to check the surface detail actually generated cleanly before I touch anything. Next, I jump into the Retopology tab. I'm switching this over to quad topology instead of triangles, and dialing the poly count down to something way more manageable, 50,000 instead of 500,000. Kick that off, and it reprocesses the whole mesh into clean quads at that lower density. And that's the result, down from 500,000 triangles to under 60,000 quads. Much easier mesh to work with once this hits Blender. Now for materials, I'm switching over to the PBR generator, which builds out proper realistic texture maps for the model instead of leaving it flat shaded. And here's the helmet with actual materials on it now. Worn metal, matte fabric paneling, way more believable than the flat base color. Quick check on the normal map again, just to confirm the surface detail held up through retopology and texturing. Let's start with a side-by-side comparison. On the left is the original AI-generated high-poly mesh, and on the right is the AI-generated game-ready retopology. At first glance, they look almost identical. The overall shape, proportions, and major design elements have been preserved remarkably well. As we rotate around the models, notice the visor, vents, side modules, and the panel lines across the helmet. Even after a significant reduction in geometry, these features remain crisp and recognizable. The reason is simple. The fine surface details from the high poly mesh have been baked onto the game-ready model using texture maps, allowing it to retain the same visual quality without carrying millions of polygons. From most viewing angles, it's surprisingly difficult to tell which model is the original high poly version and which one is the optimized game-ready mesh. This is exactly what you want from a successful retopology workflow, preserving the look of the high poly asset while making it lightweight enough for real-time applications like games and interactive experiences. Now let's switch to wireframe mode. This is where the real difference becomes obvious. The original high poly mesh is packed with an extremely dense network of polygons. Every small detail is modeled directly into the geometry, resulting in a heavy mesh that's difficult to edit and expensive to render in real time. Now compare that to the game-ready retopology. Instead of millions of unnecessary polygons, the mesh uses a much cleaner and more organized topology. The edge flow follows the shape of the helmet while keeping the polygon count dramatically lower. As we rotate around the model, you can see that geometry is only added where it's actually needed to preserve the silhouette. Flat surfaces and subtle details no longer rely on extra polygons. This optimized topology makes the model far more practical for UV unwrapping, rigging, animation, and game engines, while still maintaining the overall form of the original high-poly asset. It's a great example of how good retopology isn't about keeping every polygon. It's about keeping only the ones that matter. And finally, let's switch to solid mode. Without textures or wireframes, we're looking at the raw geometry of both models. This makes it much easier to compare their actual forms and silhouettes. Even after the retopology process, the game-ready mesh stays remarkably faithful to the original high-poly model. The major shapes, proportions, and hard surface forms have all been preserved. From normal viewing distances, it's difficult to spot any noticeable changes in the overall design, despite the dramatic reduction in polygon count. This is exactly what good retopology aims to achieve, keeping the visual shape of the original asset while removing unnecessary geometry. The result is a lightweight mesh that's far more efficient for animation, rendering, and real-time applications, without compromising the character of the original design. Overall, it's an impressive demonstration of how AI can generate a production-friendly, game-ready mesh while staying remarkably close to the original high-poly model.
So, can AI generate a 3D model from a single image? Absolutely. But as you've seen, getting a model is only half the battle. If you actually want a production-ready asset, this mesh still needs work. In the next video, we'll manually retopologize it inside Blender using a few powerful add-ons to build.
Then we'll unwrap UVs, generate AI textures, and finish everything inside Blender. Want the full AI to production workflow? Subscribe to Pixel to Poly. We're just getting started.